Welcome to the American Ceramic Society's short course on firing of ceramics. My name is Dennis Brosnan, and I'm glad that you're taking this class once again. This is class number 2, and it's about chemical and physical characterization or characterizations used during firing. So we're going to let the ceramic talk to us today in terms of physical properties. Now, before I get started, I want to make sure that you understand what to do if you have questions. First of all, you can arrange for Zoom office hours by sending me an email to the address shown, bdennis@clemson.edu. And I would ask you to propose at least 2 times on different calendar dates. And please understand that I'm in the New York time zone. So let's try to find a convenient time that we can meet. Each student is allowed up to 1.5 hours of Zoom office hours that you can use during the course. Now, I want to say that once you send me an email, I'll send you a Zoom link on one of the dates that you have chosen, and we can meet face to face. Well, you can send me a question by email at any time. I also want to remind you that you can request a PDF file of each lecture from the American Ceramic Society for review purposes. Of course, my understanding is that you can access these individual lectures or classes as you wish so that you can review as you may need to. Now, I want to make sure that we both understand that any contacts with myself and you are subject to the confidential disclosure policies and disclaimers that are given on the next slide. Now, those of you that took drawing saw this as well, but I want to remind you that in any aspect of this course, never provide me with any confidential information. I'm sure that you will follow your organization's confidential disclosure policies. I have no agreement with your organization, and I have no right or desire to obtain any confidential information whatsoever. Also, need to provide a disclaimer, meaning that I'm going to give you the best information and advice I can in any situation based on my education and experience, but I don't warrant that advice. I don't guarantee that it will solve any problems. In a very rare case, it might actually cause a problem. I don't think so, but nevertheless, you should use information from this course at your own risk and that of your organization. But I believe that I will only give you positive help. That's my intention in any situation whatsoever. Now let's review a minute from the last class and make sure that we're all on the same page. Some of the words in this slide are as follows. We have a goal in firing: to provide permanent bonds between particles, because we make our ceramics out of particulate matter. And we're going to achieve that forming of permanent bonds by using temperatures that activate any process required to form those bonds, and we call those processes sintering. Now, we also talked about how you figure out what the firing temperature should be in whatever it is that you are producing. And I want to reiterate that we came up with 3 methods last time. One is to do trial and error firings of ceramics, fire them to different temperatures and figure out at what temperature and time you get the right properties. That's a really old-fashioned manner of doing things. A more enlightened approach is to use phase equilibrium diagrams, maps that show when processes will take place. We can make educated guesses because usually in ceramics, the processes are at the point that the furnace interior is glowing red. We've achieved red heat, which is above 900 degrees Celsius. Another way to do this, in a much more enlightened way, is to use thermal dilatometry, not to determine thermal expansion coefficients, but to look at the point where shrinkage starts in the ceramic under the action of heat. Now, last time we also talked about 3 types of sintering. One was vitrification, meaning simply heating up the ceramic until a melted phase that we typically call glass forms within the ceramic. Glass meaning a amorphous or non-crystalline substance. It's somewhat analogous to window glass or glass objects that we're accustomed to, but the glass that's formed in firing clay ceramics, of course, is a very crude form of glass. And when the object cools off in the kiln, the glass forms a cement or a bond between particles. So that's certainly one type of sintering, and we call it vitrification sintering. Another type of sintering also forms a glass. It's called reactive sintering, but during the process of sintering, that glass changes in composition and forms crystalline matter. So gradually during firing, the bond in the ceramic changes from glassy to crystalline, and the glass may partially or wholly disappear during that form of sintering. The final type of sintering, which you've undoubtedly heard of in your other classes, is solid state sintering. Solid state sintering is sintering of particulate matter at temperatures where diffusion processes, meaning atom movements, can create a bond between adjacent particles. Usually there's no glass present or a negligible amount of glass, so the glass doesn't play a big role in the sintering processes. Now, the consequence of sintering is shrinkage. We have the same weight, but the ceramic shrinks. We have firing shrinkage, and that means that the density increases. So sintering achieves densification. And of course, we usually see that most of the properties of the ceramic improve dramatically at some stage in densification. And we say that the ceramic is fully mature when it's achieved an extent of firing that gives us the properties that we want in firing. Now, these property goals are set many ways. They're set by experience, which tells us that the product is going to perform its required task. And these are sometimes proprietary standards. Sometimes they're consensus standards, meaning groups of people have gotten together and said, this is what this type of product needs to exhibit in terms of chemical or physical properties in order to perform. Many of these are published by standards organizations within various countries or various organizations or groups of countries. So we have them in the United States, published by the American Society for Testing of Materials. In Canada, they're published by the Canadian Standards Association. In Europe, they're published by the European Union. So each country, Australia, Japan, has its own types of standards. There are also military and government standards that you must meet. And certainly we're not going to forget standards a customer may have for you to supply product to them. So there are various types of standards, and the goal of firing is to reach the specified properties or exceed them as given in those standards. That was last time. Now this time, we're going to talk about chemical and physical test and the numbers that they provide. You should take this class depending on your background. Now, you may be a laboratory person, or you may have been involved in industry for a long time, and you may know most of the things in this lecture. I still believe it will be useful for you to hear some of the things that I will say about these tests. But nevertheless, I hope everyone will take this. Now, characterization is a term that we use in university language to talk about chemical and physical properties that, in our case, potentially affect firing, because chemistry certainly does. And some of the physical properties and mineralogy development talks to us about the progress of firing. In other words, the progress toward maturity, with maturity being where the product has reached the properties that we want. So our object in firing is to produce a mature bond, as we call it, in the ceramic. Now, this is the way the ceramic talks to us, with numbers. Ceramics don't make very many sounds. They do make some sounds when cracks occur, as in thermal shock cracks or cooling cracks in a kiln. There are people that have measured acoustic emissions during firing of ceramics. But mainly what I'm talking about is numbers. Numbers talk to us, and so we have to get comfortable and very familiar with what these numbers are and what they mean. One way to look at these is to go to your corporate library. You might have this book by Dennis Dinger. Dennis was one of my associates during my very active teaching years, a professor of ceramic engineering, and he wrote a series of little books. This one is called Characterization Techniques for Ceramists. I know it's available on Amazon. You may have other books in your corporate library as well. There's certainly a lot of resources available from the American Ceramic Society. So if you want a little book that covers most of what I'm going to say today, I would recommend this one right here by Dr. Dinger. So I'm going to start out with some practical examples. I'm going to use some product data sheets just to explain kind of where we're going. So I took one from a raw material called Actamin CG, that's catalyst grade kaolin. So this is something you would buy in a bag or a super sack that you would use in batching and making a ceramic. And so there's some information here that's useful to you. Of course, the moisture content is very useful. You certainly want less than 1% moisture to have a free-flowing powder. That's probably on an as-received weight basis. In this particular material, there's a particle size criterion, maximum amount retained on a 325 mesh or 44 micron diameter opening screen of 1%. So these are some numbers, but I really want to focus on the chemical analysis. So look at the typical chemical analysis on this data sheet. Silica, percent, average 45.6. Well, there's plus or minus there, a little variation that they allow themselves to take. It's a natural material, so there's going to be some variation. Alumina content, weight percent. These are in weight percent. Typical chemical analysis is 38.4%, plus or minus a little bit. A little bit of iron oxide, and it's very low, about 0.65%, plus or minus a bit. Iron oxide is important because it's a flux in firing ceramics. In kaolins, it also tends to make them change in color as they are heated. It can color the final product. There's some TiO2, titania. That's a constituent of the ceramic chemically. It's about 1.8%. And most of the times when you have kaolin, you're going to have a little titania because it's naturally in the soils and the raw materials. Importantly here is alpha quartz. That's crystalline silica, SiO2, less than 1%. That really affects the firing process, and we'll get to it later on. Now, if you add all those numbers up on the product data sheet, you get about 86.3%. Well, where's the rest of this? Well, on the right, you see an X-ray fluorescence, XRF analysis of the same kaolin from one of the classes that I taught. You see alumina, 44.81%. Well, that's about 45%. You see silica, 50.67%. In that case, it's a bit higher than the silica on the data sheet. And you see a lot of other constituents there that are present in the full chemical analysis. Well, this full analysis was not really necessary for a product data sheet, which is showing you typical values. The chemical analysis gives you minor constituents as well. But if you add all those up, we're going to be pretty close to 100%. Now, I'll be frank with you, I didn't add them all up. Some of the numbers in brackets there are below the detection limit of the device. And typically you'll see that when they're below about 1% or so. So the key question is, what's the difference? Why does the active minerals product data sheet add up to about 86% and the analysis in my lab add up to 100%? Well, the answer is the weight basis that these numbers are expressed upon. So there's a test called loss on ignition. It's the loss in weight expressed as a percentage when a material is heated up, typically around the world, to 1,000 degrees Celsius, okay? 1,000 degrees Celsius will decompose most of the minerals that are present. And as you'll see as we go along, kaolin will in fact lose hydroxyls as water vapor as it's heated up to below 1,000 degrees Celsius. So the theoretical loss on ignition of kaolin as a mineral is 13.95%. In this particular case with the CG kaolin, you can see that I came up with a number of 14.83%. So I came up with a little higher loss on ignition than theoretical kaolin. Well, the actual product probably contains a little bit of carbonaceous matter. There could be some other minerals present that in minor percentages that lead to a little weight loss. So we're just slightly higher. So if you go back to the previous slide, the sum of all the minerals in the CG data sheet was 86.4%. If I add in my loss on ignition of 14.8%, then I come up with slightly better than 100%. So here's the deal. Back here, when we were looking at these product data sheets, the CG kaolin was expressed on an as-received weight basis, okay? Whereas the expression from my laboratory factored in the loss on ignition, and so my result is on an ignited weight basis, okay? Ignited weight basis or constant weight basis on heating. So you can see that I've come up with a little bit different number than you had before. And I'm just want to make sure that you understand. So you can always look at a data sheet and add up the numbers. And if they add up to 100%, as in this case, then it's likely to be a calcined weight basis or ignited weight basis. Whereas if they don't, they're probably on an as received weight basis. So that's what's happened. We've measured in my laboratory the loss on ignition, and that explains the difference in the weight basis. Now, the chemistry doesn't show us the mineralogy. If we use a technique called X-ray diffraction, I'm going to talk about that more in just a minute. X-ray diffraction tells us wherever X-rays are bit in certain characteristic ways by the mineral. In fact, it's reflecting the crystal structure of the mineral. So there's the pattern of CG kaolin, and then the computer and the instrument is matching peaks here between things in its library, things that it knows, versus peaks that we get in the actual X-ray diffraction test. And it matches up kaolinite pretty easily. Well, that's good news for us. The computer also identifies biotite or mica. Now, you know, mica is a source of alkalis, and so we believe that from the minerals that are present in kaolin, biotite or a micaceous material would be a common impurity in the kaolin. Now, notice that the X-ray diffraction test, which identifies minerals, did not identify any quartz. And that's the good news. And the data sheet for this CG kaolin said that we had less than 1% quartz. So that's why the X-ray diffraction did not identify it. Now, here's another product data sheet. And by the way, I don't believe that CG kaolin is available on the commercial market today. I have not tried to keep up with it, but I think that company was either bought or absorbed or something like that. Here's a product I made early on in my career called Paratex. Paratex is a fired or sintered refractory brick product, or at least it was. I'm sure it's not made anymore. But it's a 95% MgO class fired or burned refractory brick. And you can see, if you look closely down here, that it contains 94.9% MgO, a little bit of calcium oxide, 1.6%, a little bit of silica, 1.9%. Those are the fluxing oxides that help Paratex be burned and form a refractory material. A little bit of alumina, and maybe some traces of other materials. So that manufacturer is trying to show the chemistry to show that it meets a certain classification that was present at the time this product was made, published by the American Society for Testing and Materials. You can see that there is a bulk density figure here given in both inch pound and metric units, and there is an apparent porosity figure given here, 15 to 18%. Now, this should be typical. It doesn't mean that every brick that was ever made called Paratex had less than 18% porosity. There were probably some that were under-fired, so to speak, and weren't mature, and maybe a little bit lower. But you should expect the average Paratex brick to be in the area of 15 to 18%. There's compressive strength data for Paratex. Please ignore this column. It's for this other product, which we're not thinking about right now. There's a modulus of rupture. That's the strength in three-point bending. I'm going to talk about modulus of rupture in a minute, but it's just a strength value calculated as the maximum stress on the tensile side of the specimen at failure. Modulus just means typical. There's no particular significance to the use of the word modulus. Just interpret it as meaning typical. There's a reheat change value for the refractory at a particular temperature. This is a way of characterizing most refractories because you don't want them to shrink in a furnace lining at the use temperature significantly. Otherwise, brick joints will open up and other bad things will happen. And there is some refractoriness test, refractoriness under load in this case. So most of our products that we have will have a product data sheet, and most of the raw materials that we have will have a product data sheet as well. We know in the United States, we have material safety data sheets, which talk about the constituents that go into products, and that provides some information. And in other parts of the world, you will have your own types of safety data sheets. Okay, well, let's get started. We're going to talk about some of the techniques here of chemical and mineralogical analysis and some of the numbers that they give. And we're trying to make sure we're on the same page. Now, I realize that you have likely taken other courses in this sequence and that other instructors or professors have talked to you about these topics. But I wasn't with you and I don't know your background, so I'm going to go over these things and provide my own insight into how these things affect firing. So, part one, chemistry. These are the elements that we talk about. And a lot of the things that we talk about are some of the elements in this group: magnesium, aluminum, silicon, for example, are there. We get into the transition metals. We get some of the oxides that we've talked about that sometimes form fluxes or sometimes they're fairly refractory. There are other substances like zirconium that you're using in forming ceramics. So I understand this. Very rarely do we get into many of the very heavy metals or the lanthanide and actinides. So the alkalis are generally fluxes in the ceramic, and they tend to flux some of the non-medicals like silicon dioxide. We're going to talk about all this. So really, out of this large group of elements, we're typically, for most ceramics, talking about just a few of these. So these will bond together and form crystalline substances or unique substances or minerals, either natural minerals that we can mine or artificial minerals that we can make. So that's our starting point in our kitchen where we're going to make a ceramic. Now, I want to talk for a minute about oxide analyses. This is the same substance. So on the left, I've shown you an elemental analysis, the elements that go into a ceramic. And on the right, I've shown you the same chemical composition expressed as if all the elements were there as oxides. Now, I know that it's possible that they're not all there as oxides. They usually are in most of the ceramics that we make, but we make things without much oxygen as well, like silicon carbide, so silicon nitride. So nevertheless, I want to say that these are the same substances. So you can convert from an elemental analysis, which you're likely familiar with if you're a chemist, to an oxide analysis if you're a ceramist or cement chemist, whatever the case may be, by using oxide factors. You can Google oxide factor and find a list of these. So we can take the aluminum content, multiply it by a factor, which is just the gram molecular weight of aluminum oxide over the gram molecular weight of aluminum, and we'll get the aluminum oxide content. Usually when we go from a conversion of the elements to the oxides, we're going to normalize this result to 100%, just so that it makes it more convenient for us. So there's some things here that you need to know. For example, in an X-ray fluorescence analysis, the analysis, depending on your equipment, may be blind to sodium. Okay, so it's not shown on this analysis. Well, excuse me, there it is. But if I was using an X-ray fluorescence, an older fashioned one without some inert gas shielding or a vacuum or whatever the case might be, I might not see sodium. Had a case in my career where a company was making a product and they said there's no sodium in the product. I said, well, show me the analysis. They showed me an analysis and I said, there's sodium in this product. I know it. They said, no, it's not. So I got in the car and went up to the lab that they used and looked at the equipment. I knew instantly why they were not reporting sodium, because their equipment was not capable of detecting sodium. It was there. So we got a proper analysis, and that was the end of that. Now, notice the chemical analysis also tells you total silica that is present. In ceramics, we can have silica present as a glass. We can have silica present as a crystalline substance, and that crystalline substance can take several forms. several minerals that can be formed. So on this analysis, this is the total silica. Sometimes you'll see an expression of free and combined silica. Free silica is silica that's going to be a particle, like quartz, that's hanging around within the raw material. Combined silica is silica that is part of the compound or mineral that's making up the ceramic. We're going to use oxide analysis, of course, in this particular lecture because that's the most convenient thing for us to do. Now, the prior slide gave the chemical analysis, either elemental or oxide, for the mineral kaolinite. It has a formula, alumina dot 2 silica dot 2H2O. The dot is used just to express these in molecular forms. You could express it as a compound using elements if you wanted to. That's okay, but as you'll see when we get into phase diagrams, we like these ratios here to be expressed in the chemical formula because they tell us a lot about what potentially will be formed in firing of the ceramic. Now, kaolin is formed by the geological decomposition of rocks over a long, long period of time. Feldspathic rocks form kaolin. So a little bit ago, we found biotite mica in the CG kaolin X-ray diffraction. That's to be expected because feldspathic rocks contain micaceous material. Usually kaolins contain some mica. So they're major constituents of alumina and silica and water. It's not really present as water, but we call it that. The OHs, the oxygen and hydrogen, are combined in kaolin as hydroxyls in the crystal structure. And of course, when kaolin's heated, those hydroxyls are going to come zinging off. They don't like being by themselves in the atmosphere, so they combine with hydrogen immediately and form water vapor coming off. Now we can classify those constituents as major constituents, alumina and silica. And some of those could be fluxing oxides like soda, sodium oxide, potassium oxide, calcium oxide, which I call lime all the time, magnesia, MgO, and FeO, if it were present in that valence or oxidation state. In other words, reduced hematite or red iron oxide becomes woostite or FeO. We have some coloring oxides that are there, the irons and the titania. Sometimes the lime will combine with titania and form specific colors called sphenes. Those are the mineral forms. So not shown on the analyses that we have were anything less than about 0.01% by weight, or things the XRF is incapable of detecting, like sodium, as I said before. Most people accept the detection limit of XRF units as 0.01. It can be lower. It depends on a lot of factors that are instrumental in nature. We don't show any carbon or other ignitable substances in the composition. So that's typically going to be what we see in a composition. Now, here's another reinforcement. We already talked about a calcine weight basis, but you can see if kaolin, given the theoretical formula, decomposes into a substance we would call metakaolin. You'll learn more about this when we start talking about sintering aluminosilicate ceramics. It will kick out a silica molecule and it'll kick out water. So you can calculate the loss on ignition of 2 times the molecular weight of water divided by the gram molecular weight of kaolinite, and that turns out to be 13.95%. And so we use that in converting between a as received weight basis and a calcine basis. On to X-ray fluorescence. How do we obtain that? Well, we obtain it in an instrument that generates X-rays and bombards the specimen down in a specimen holder within the instrument with X-rays that puts energy into the elements in the target where the X-rays are striking, and the target emits characteristic X-rays. Characteristic means they're X-rays of given wavelength or energy. So these X-rays are generally monochromatic, meaning one wavelength that hit the target, and then the target itself, the ceramic that we're analyzing, emanates or releases, if you want to call it that, other X-rays that are characteristic of what is in the target. So we can take those X-rays that are given off and analyze them as to energy or wavelength, and we can figure out what's in the target. And the intensity of radiation coming off of the specimen tells us how much is there. So what it tells you and what it doesn't tell you, XRF, X-ray fluorescence, is it tells us the total silica. It doesn't tell us the free quartz, okay, or the combined quartz. It just tells us the total. It tells us the flux that's present. Particularly, I've highlighted sodium and potassium, and that tells us about the tendency of the ceramic to vitrify or shrink on firing. But it won't tell us the sodium if there's no vacuum or inert gas shielding. It may tell us the total sulfur, but there are other methods called the LICO method. We'll talk about that in a minute. It doesn't tell us anything about soluble species or carbon. It doesn't tell us the loss on ignition or the mineral type. It does tell us a little bit about the potential to color when fired, and color mainly comes from the transition elements that are present in the chemical composition. Remember that you can pause any of these slides at any time and think about it or review as you need to. Now, I mentioned carbon and sulfur. The standard method throughout the world is the LICO method. The instrument named LICO is lent its name to the method. And that means that we simply insert the specimen and burn off the sulfur and the carbon. And there's an infrared means of detection of the sulfur gases and the carbon monoxide, carbon dioxide that's emitted in igniting that specimen in air. And that tells us how much carbon is there. This is a standard method in analysis of materials. And so you can look up the method if you're interested in it. But just notice that carbon and sulfur are not determined accurately, or maybe not at all, by X-ray fluorescence. Now, the chemistry is the chemistry, but it doesn't tell us the mineral constitution. To determine the mineral constitution, we need to use a method that's sensitive to the crystal structures of minerals that are there. And we want to identify the mineral. Quartz has three forms: alpha quartz, tridymite, a different structure, and cristobalite. And in ceramics, we're very interested in these substances because there's a volume transition when quartz is converted into tridymite and to cristobalite. There's a density difference between these minerals. The density of cristobalite is the lightest or lowest, so there's a big expansion in going to cristobalite. The method is simply to bombard X-rays in a beam onto the specimen, to rotate the specimen so that it will generate X-rays, or these X-rays will be bent or diffracted in certain characteristic ways, certain characteristic angles that depend on the crystal structure of the material that you're looking at. And by analyzing those diffracted X-rays, we can tell what is present. So I showed you an X-ray diffraction analysis pattern before. Here's the pattern from an instrument in my laboratory. And it's identified right here by the library pattern that's given to us. So the mineral identity in this case is determined by taking a known library pattern, fingerprint, if you want to call it that, of quartz, and comparing it to what you've got. And then you can determine what is present. X-ray diffraction analysis. So X-ray diffraction analysis has a limit of detection of about 1%. Okay, so if you have something present that's there below 1%, you probably have to use another method to figure out what it is. Now, when I was a student, we didn't have the computers that we have today, so we had to get a pattern on a machine and compare it to index cards that had diffraction patterns on them. There was a little system of doing that, of going to the major peak, the highest intensity peak, and then figuring out what all these other peaks were. But it was laborious and less accurate. So computers have made a big difference in the speed and the accuracy of analysis. Well, just like XRF, X-ray diffraction, XRD, tells us certain things, and it doesn't tell us certain things. It tells us the identity of the minerals present above a concentration of about 1 weight %. It tells us free quartz, but it doesn't tell us much about glass that may be present. Now, those familiar with X-ray diffraction know that there are some low angle X-rays diffracted by glass, and the amount of glass can be estimated by modern up-to-date machines, but it doesn't tell us much about the glass. It can be used in quantitative mineral analysis. That makes it very useful in comparing chemistry to mineralogy. To the next lecture, next time on X-ray, on use of phase equilibrium diagrams. Then we're going to talk briefly about physical properties. I don't have time to do all of this. I'm going to assume that other lectures involve testing, but we're going to highlight density, how to measure it, why we measure it, because densification takes place during the firing process, and we need to fire to the extent that we achieve a mature ceramic, which usually means a certain fire density goal. We're going to talk about porosity and pore size distribution. So we're going to talk about some porosity terms like apparent porosity. That's the porosity that we can measure by some penetration method where a liquid will go into the pores, and that's how we measure the amount of porosity that's there. We're also going to talk about measuring the diameter of the pores that are present, because this tells us a lot about the maturity of the ceramic, and it certainly affects the performance of the ceramic. We'll talk about strength. We'll talk about compressive and bending strength, and a way that tensile strength can be easily measured in the laboratory if that's something that is of interest to you. And of course, strength is a measurement of maturity, because typically ceramics gain strength during firing as they densify. Densification does something to increase the modulus of elasticity, the ratio of stress to strain of the ceramic, and that's directly related to some of the strength values that we have. Finally, I'll briefly talk about ultrasonics and the velocity of sound. These are very useful in production situations to gauge the maturity that you've achieved in the ceramic. I will say that here's one of the books that you might find in your library. It's an older book now, written by John Jones and Mike Berard. It talks about most of the subjects that I'm talking about today. It's a good introduction if you have no background in ceramics, and you can find this in your corporate library or from a university library, or perhaps you can buy it on Amazon or from a used bookseller. So let's begin talking about this. And well, density. Density is weight per unit volume. And There are several terms that we use, so we can express it in inch-pound units or metric units, however you like to do that. But the first of these terms is bulk density. That's the weight over the bulk volume, the physical dimensions of the ceramic part. And so the bulk volume includes open pores and closed pores, pores that have been closed in the firing process. So the bulk density is that of the bulk, meaning the weight divided by the bulk volume of the ceramic. It's usually the lowest density. Then there's the apparent density, the weight divided by the apparent volume. That means that they're excluding the open pores. So that would include the weight divided by the volume, excluding any open pores that we can penetrate. That gives you a little bit of analysis capability, because you can compare apparent density to what's called the true density, and you can figure out how close you are to fully densifying the ceramic. Of course, the true density, sometimes called the ultimate density in today's world, is the weight divided by the volume excluding all pores. So I've given an example for bricks here in each one of these, just because I hung around and worked with bricks quite a lot. But if you take the bulk density and divide it by the true or ultimate density, you'll get the percent solid. So the percent not solid in this case is 8.8%, right? 8.8% porosity in the example that I've given you, total porosity. So those are terms. Generally, you'll have a density goal, and it may be bulk density or it may be true density, but it's going to be one of those that you have in densifying the ceramic. Now, density terms also apply to powders. And here's an example of a porous fragment taken from one of the really good ceramic textbooks. And it tells us about the weight of the particle, the closed porosity, the open porosity, the ultimate density, 2.62, the apparent density, and the bulk density of the powder. So these terms apply both to fired goods and to powders that you might be using as a constituent of the ceramic. Now, there are several ways to determine density. The old-fashioned way is to weigh the ceramic on a scale and measure its volume, measure its dimensions, compute the volume, and the weight divided by the volume is going to be the density. It's the least accurate because of measuring errors. Another means to do this is water displacement techniques. Sometimes these are called Archimedean techniques because the determination uses Archimedes' principle of buoyancy. Another way is to use a pycnometer for calculating the true density. That's a water displacement method. We'll not talk about that, but that's one way of determining true density. And finally, there's the mercury displacement methods, which include mercury porosimetry. I will talk about that. So the water displacement method has you measure the dry weight, saturate the specimen with water and measure the weight wet. And then you take the wet specimen and suspend it in water and measure its suspended weight. And you can calculate the bulk density, the apparent density, and the apparent porosity using these little formulas right here. So this is much more accurate than weighing and measuring the previous technique. And it's the way that most ceramics are tested for density. Since it's more accurate, it doesn't contain physical measurement errors. Well, why are we concerned about density and porosity? This is a graph of porosity volume, okay, versus firing temperature for various fire clay ceramics. Remember, fire clays are substances that usually contain aluminosilicates or kaolinite type minerals. And you can see, just following one of these graphs, as we raise the firing temperature, as we get above about 1,000 degrees C, then rapidly we're going to get a reduction in porosity. There's an accompanying shrinkage, an accompanying increase in density that we have in the ceramic. So that's very typical behavior for a vitrified ceramic. And most types of ceramics that we manufacture will exhibit some shrinkage at certain temperature, minimum temperatures that cause the process to take place. I like this graph taken from Grimshaw's book because it shows that some fire clays exhibit shrinkage followed by an expansion. That's really interesting, and it may indicate that there were gases released, maybe from carbonates in firing after the glass formed, and these bubbles cause bloating in the ceramic and cause it to appear to expand. But even if it's not a clay ceramic, we do exhibit expansion in some of our materials when reactions take place. This is certainly true in a lot of ceramics that form new minerals that are lower density than some of the minerals that we started with during the firing process. Okay, there are two quantities that we're concerned with respect to pores. And both of these change during firing. The amount of porosity typically goes down in firing as the ceramic densifies. But the sizes of pores change as we fire the ceramic. Now, most of the particulate ceramics, the size of smaller pores in the ceramic is about the same size as that of the particles in the ceramic. Now, most of the ceramics can also contain macropores or bigger pores due to packing defects that you have in the ceramic. So we can have two sizes of pores predominate in the ceramics. But typically, the smaller pores tend to get bigger during firing, and the bigger pores tend to get smaller. So by looking at the sizes of pores, we're actually tracking the progress of firing. So the amount of porosity goes down, but the sizes of the small pores goes up. Pores consolidate in firing, small ones, and larger pores might be eliminated in firing. So pore sizes become important to us in figuring out what we've got. So to determine pore sizes, we put fragments of the ceramic in a chamber that's pressurized, usually containing mercury. You can use helium for very, very small pores, but mercury is used for most micron and submicron size pores. There's an equation called the Washburn equation, which relates the applied pressure that we see as mercury is forced incrementally into this pressure chamber. We can determine the size of pores that are being intruded with mercury at any particular time. Now, at low pressure, we simply surround the particles with mercury, and we know the weight of material that we have in here, and we can figure out the volume. So we get a true density or mercury density value. What the experiment is to intrude, using pressure, intrude the mercury into the ceramic. You know, mercury is a hazardous substance. It evaporates at room temperature. And so the people that do this are very familiar with the safety protocols in performing mercury porosimetry test. So here's a mercury porosimetry test result. This is a molded brick. And this is expressed as incremental intrusion versus diameter. So diameter on the bottom axis, we've got 100 microns, 10 microns, 1 micron and below. And this is the volume of intruded mercury. So if you look at this in increments, we can see that at fairly large pore sizes in this particular brick, we had a band of pores around 100 microns. And as we got down to the smallest band in the area of 1 micron or so, less than 10 microns, we got a large band. Very typical for a brick product. This is a bimodal particle size distribution. Bimodal means 2 sizes of pores within the ceramic. Okay, a brick is not a very dense object, and so therefore we maintain some of the fine pores. But if we kept on firing this brick, this peak would lower in intensity, and this peak might also lower in intensity. So we'll tend to coarsen pores. So we'd have some other peaks show up in this area. Some of these peaks would get larger in intensity during the firing process. We get a certain data output from our mercury pore symmetry test. It gives us a bulk density and apparent density values, but I just wanted to highlight the apparent porosity in this product was 11.2%. That's the amount of void space within the ceramic. But then we can characterize the pore sizes. Less than 10 microns, we had 82%, less than 1 micron, about 23%. So there's a big band of pores in this 1 to 10 micron area, and you saw it on the previous graph. Just go back and look at it if you want to, and you can see that. So pore sizes make a difference. I want to tell you a little story about a refractory product called Ruby. It was an alumina chrome brick, about 90% alumina and about 8 or 9% chrome by my memory, chromic oxide. It was red in color, like a ruby, because it was a fired brick and it formed that alumina chrome solid solution, having that red color. When it was initially used in incinerator service, it exhibited a fair amount of spalling in that particular service. And so someone at the manufacturer's location, I was told, decided, what if we underfire the ruby? What if we maintain finer pore sizes in the product? Would it be better? And it was. And so then they called it Ruby SR, spall resistant. So there was no thermal spalling in the product in the furnaces where it was used, or at least it was minimized. And if the story that I was told is true, and I think it is, they simply underfired the ruby and came out with another product, which was a little cheaper for them to make, and they solved a problem with their product. They solved that problem by engineering the pore size distribution in the product. They were smart enough to do that. So pore size distribution makes a very large impact in the performance of the product. The Ruby product, as it originally was made, was a very mature ceramic. It's what people thought a mature brick refractory brick should look like. And they came along with new technology and said, oh, let's make it a little different. And it was much better. So that, as I mentioned, pores grow during sintering. The small pores grow at any rate. If you have macro pores, they may diminish, at least in extent, to some degree during the consolidation during sintering. But pore growth during sintering is a way to figure out what temperature at which somebody made their product, in addition to thermal dilatometry. But pore growth and sintering of higher purity ceramics is the way that that I've done that. So that's why we need to know about pore size distribution, since it changes. Now I'm going to make just a few comments about strength, not very many. Of course, we have compressive strength. There's a brick being tested for its compressive strength. It actually breaks by tensile splitting. If you look very carefully, you'll see that during the failure of the ceramic, we get vertical cracks in it, and it's trying to form a pancake shape, so to speak, pancake or rounded shape on the ends. And the rounded shapes rounded ends break off in the test, and we get these vertical cracks. Compressive strength. That's important in bearing strength in a ceramic. But we also want to measure tensile strength in ceramics, and that's hard to do. So the center picture is a 3-point bending test. The ceramic, in this case a brick, is supported on 2 points, and an upper ram comes down and contacts the ceramic, and pressure is applied to break the ceramic. That's just like this diagram right here, which is a little easier to see. The load applied in the middle and the support being on the ends. And by calculation, we're able to determine the maximum strength at failure in the surface of the ceramic. Okay, and that surface that's in tension is the lower surface. I hope I said that right previously in the lecture. And because the ceramic is trying to bend or deflect because of this load in the center, and that forms a tensile stress in the bottom of the ceramic, the lower surface of the ceramic part. Okay, if you use a calculation, then you can calculate that maximum tensile stress or fiber stress in the ceramic at failure, and that's called the modulus of rupture, the typical failure in bending. Now, some ceramics use maybe 4-point bending, 2 bottom supports and 2 upper supports applying the load. Some use 3. It's also possible to estimate the tensile strength of the ceramic by compressing a cylinder on its side, and that's the same as pulling it apart from a stress standpoint. So we get a maximum stress at failure called a diametral compressive strength, which is actually like a tensile strength. You can measure tensile strengths of ceramics. It's harder to do because typically you have to form a specimen that you can grip in a machine's vice grips. Now you can measure these at room temperature and high temperature and compare room temperature and high temperature results, and that gives you some more information, which I don't have time to talk about, but nevertheless, strength measurements are important. The reason they're important is strength increases as you fire the ceramic. So here's some data from Grimshaw. It's an old book on chemistry and physics of clays. This was for a fire clay ceramic. And you can see strength values at various temperatures, and they're pretty uniform until you get up in the area of about 1,000 degrees Celsius. And at 1,000 degrees Celsius, we've actually performed some reactive sintering. There's been some melt form and new minerals formed between the fire clay particles. And as we continue increasing the temperature, we're going to get very dramatically higher strength. So strength increases as a function of temperature, depending on the sintering mechanism, the type of sintering that we have going on. So I hope that you will find this at least interesting. That's why we look at strength and have strength goals in firing of ceramics. Now you'll notice that I've thrown in a normal statistical distribution where most of the strength values are around an average. So this is a frequency distribution. So most test values are up here and the least test values are down here on the tail end of this distribution. And so we typically call this a bell-shaped curve or normal statistical distribution. And most of the ceramics I've made follow this normal distribution because they were brick products and traditional products that were fairly porous. Sometimes when you get to technical ceramics or high-tech ceramics, they will follow other distributions like the Weibull statistical distribution. And so the normal distribution wouldn't apply. But the point of this is that we're going to get test values in testing a ceramic, and individual values might not be sufficient reason to say that we're not firing properly. So we measure statistical values in the normal distribution by plus or minus 1 standard deviation. And plus or minus 1 standard deviation is going to cover 68% of the test values that we normally would expect. Now, I'm not trying to make a statistician out of you. but I am trying to reinforce the point that we need to think about statistics. So you can calculate a standard deviation pretty easily, and here's some test values. They're not lined up properly, but that's okay. So you can add all those up and you can compute an average. That's 5 values. Now, if you're using a statistical calculator, we also get a number for the standard deviation. Now, I know that some people are well aware that there's a certain number of test specimens to be tested that are significant. In this type of product, a brick product, the American Society for Testing of Materials says that 5 values are sufficient to understand the product. It may not be for your type of product. But now if we have the average and we have the standard deviation, we have a lot more information. We don't just have the average, we have a lot of information about the spread of data. So we can compare things. And here are 2 sets of test values. These are compressive strengths, and we have an average of 3758 pounds per square inch here in inch-pound units. We have 8699. Let me get this right. We have 9609 pounds per square inch average in the first lot. We have 8699 average in the second lot. So if I only looked at average, I'd say the first lot was better. Stronger on average. So that sounds good. But look at the standard deviations. 3759 here for the first lot, lot number 1, and 1382 for the second lot. Now you're able statistically to calculate something called a coefficient of variation, which is the standard deviation divided by the mean times 100. That means the standard deviation is a certain percentage of the mean. For lot number 1, it's 39%. For lot number 2, it's 16%. So now we have 3 parameters that are talking to us about our strength value and how good it is and what it means. And actually, lot number 2 is the better lot. It has less variation in the test numbers, even though the average strength was a little bit lower. And that's something that you can see time and again in fabricating a ceramic. Now, understand that your goals are set based by smart people, including yourself, that tell you a lot about what the ceramic should be. But nevertheless, you need to be always aware of variation in test values. Okay, finally, I'm going to talk about ultrasonics. Ultrasonics will put energy into a ceramic in terms of ultrasonic pulses, and then we can measure resonance frequency, as in measuring modulus elasticity, or we can do sonic velocity tests. Sonic velocity tests are easy to do in a plant situation. The velocity of sound going from one place to another. There's a certain distance or thickness of the product, so it takes a little bit of time for the sound to go through, and electronically we can measure that time pretty easily. And the better particle-to-particle bonding that we have, meaning the more density, the faster the sound's going to go. So it's pretty simple. So ultrasonics are used a lot with products as they exit the kill to determine their quality without having to send them to a laboratory. So it might be a quality control test. Here's a example used by one particular brick company where a brick is placed with the ultrasound going through the thickness of the brick, the height of the brick, as that we would call it in the brick industry. There's an exciting device here. And there's a recording device or detection device here. The sound is going through the depth of the brick. We're going to receive that depth, and velocity of sound is the distance divided by the transit time. Now, in that brick example, here's some velocity of sound information given versus 5-hour boiling absorption, water absorption. So the thing you should know is that density is increasing as we go down and the velocity of sound is increasing. So the density and velocity of sound are directly related. The orientation of the brick has some difference. That was the purpose of this slide, or the size of the brick. But in particular, if there are cracks in the brick, then it's going to reduce the velocity of sound and you'll find something wrong. Now, this particular brick company is run technically by some very smart people, and they will test bricks from the top of a kill car setting and compare the values of velocity of sound to the ones in the bottom of the kill car section or the center of the kill car. And they'll know how even the heat was in the tunnel kill where the brick was manufactured. So what are they doing? They're testing maturity. That's it. They're testing uniformity and trying to do a good job of making the products to send to their customer. So we're at the end of today's lecture. We talked a bit about chemical composition. We talked about how it's expressed, but we really are trying to get to the fact that the chemical composition affects vitrification and the mineralogy, the mineral composition of the product that you're trying to make. We've talked about measuring that mineralogy, but we particularly tried to emphasize today physical test. Density increasing as you approach maturity. Porosity decreasing as you approach maturity. Small pores generally increasing in size as you approach maturity, and big pores somehow decreasing in size. Sometimes this is called pore coarsening of pores, getting larger as you approach maturity. We talked a bit about variation in physical properties. It's beyond the scope of this course to really talk about statistics in manufacturing. I'm sure that your company may have statistical process control programs that offer you resource people in your company to talk about this. And we talked just a bit about ultrasonics in manufacturing and how they can be used. Okay, so the next class number 3, is going to be about phase diagrams and sintering. So I'm really going to take each of the sintering mechanisms, vitrification, I'm going to take reactive sintering, and I'm going to take solid state sintering, and I'm going to show you how phase diagrams can be used in that regard. Now, the American Ceramic Society has pointed out to me that they offer a lot of phase diagram resources. For example, they have a complete set of phase diagrams available to you in electronic form that's available for purchase. And it's likely that somebody in your company has all of these phase diagrams. You can buy books or hard copies from the American Ceramic Society. There's a website address for that. There's a really good chapter on phase diagrams offered to you for free, given the web link right here. I took a look at it and I highly recommend it. And then the book that I mentioned in the first class by Bergeron and Risbud is available for purchase from the American Ceramic Society, and they're going to offer you a discount, hopefully, since you're taking this course. Now, the phase diagrams that I'm going to use in the firing course are going to be limited in number, and so I'm going to supply these to you that you would have available. But if you're making something that isn't covered by one of the phase diagrams that I offer you, then you can obtain them easily here. Also, if you look at this website that gives a free chapter on phase equilibrium diagrams, The way that I'm going to use phase diagrams is pretty simple. Most of the books that teach phase diagrams teach about cooling from a melt as to a point where you begin to crystallize material from the melt and you cool down to room temperature. I mentioned in the first class that everything I ever made, I started out with particles of different composition and heated from room temperature, but upward in temperature. And that makes it a lot easier and simpler for you to think about. So I'm going to explain firing processes by using phase diagrams. It's pretty easy. Phase diagrams are just a map. I'm not going to try to make you an expert in using phase diagrams, but simply make you knowledgeable. So review any of these parts of this lecture that you find necessary to review. I wish you well, and we'll have our next class on centering and phase diagrams. I'll look forward to being with you at that time.